chi-square goodness of fit test compared to chi-square test of independence. And students often get these confused. And they shouldn't be, because they're two completely different tests, but they do fall under the chi-square family. So I think that leads to the confusion. But anyway, the goals here when we use a chi-square goodness of fit test is when we have a categorical variable, and we want to measure how well a statistical model fits our set of observations. So what is given would be something like a theoretical probability distribution. And I think really, if you're familiar at all with AP scores, if the probability distribution for AP scores, I forget the percentage who typically get a 1 and typically get a 2, 3, 4, and 5, and so on. Well, if you wanted to compare your observations, maybe from a local school district, to see if it fits the distribution for the national data, then this would be a test that would be something that you would consider using. So again, it compares sample data, our counts, our percentages, to a theoretical distribution. Contrast that to a chi-square test of independence, which just compares or examines the relationship between two categorical variables. So our null hypothesis is typically that a lot of times it's just that our first percentage is equal to our second percentage is equal to whatever k is the number of groups here. It doesn't always have to be like that. In fact, the example that I'm going to use here actually has different claims for different groups of the population, which will be, circling back to my previous example on AP scores. That's what you would expect. You wouldn't expect the percentage of 1s to be the same as the percentage of 2s, 3s, 4s, and 5s. You would think they'd be different. So let's just dive into, and the alternative is at least one of these P's is different than the expected value. Now, this specific claim where our percentages are equal, that's something that you would see if you were looking at like maybe observed counts over days of the week. If you wanted to see, for example, that the number of patients that enter the hospital on Monday, Tuesday, Wednesday, regardless of the day of the week, all 7 days is the same, then we would have P1 equal P2 equal P3, 4, 5, 6, 7. But if we wanted to test that, double the patients are enter on Sunday, maybe people come into the hospital on Sunday because they don't want to go to work on Monday, I don't know. And then, you would have a variation in these P sub i's. So I think this will be better instead of me just kind of talking it through and all these different possibilities. Let's just dive in and look at an example. So a medical report claims that 60% of patients report no regular exercise, 25% report sporadic exercise, and 15% report regular exercise. So do we fit the first criteria for goodness of fit? Well, actually we fit the first two, right? We have a theoretical distribution, a theoretical claim, and we have categorical variable, because the categorical variable is what? Your exercise status. No regular exercise, sporadic exercise, or regular exercise. So a hospital administrator feels that the percentage of patients in their region or their hospital, however it's framed, may be different. Collect a random sample of 470 patients. Evidently, they asked them this question, and they find that 255 report no regular exercise, 125 sporadic, and report regular exercise, whatever that is. There were 90 of those. So again, chi-square goodness of fit, because we are comparing observed data from this hospital to a theoretical distribution or a kind of a nationwide claim. So my null hypothesis here would be that P1 is 0.60, P2 is 0.25, and P3 is 0.15. H sub A, at least one of these percentages, is different. Now, the observed frequencies are obvious. 255 reported no exercise, 125 reported sporadic, and 91 reported regular exercise. The expected frequency is what we would get under the null hypothesis. So if P1 is truly 60%, then 60% of our 470 in our sample, which is 282, should be in this cell right here. 25% of our 470 should be in this cell, and 15% of our 470 should be in this cell. So our chi-square test statistic, again, we're going to do this using technology, but it's easy to calculate those up. It's the observed minus the expected squared divided by the expected. So sum all those up and we get a test statistic of 8.46. You can use the way I demonstrated previously. In a previous video, we could take put the p chi-square and put 8.46 and get a p-value of 0.015. So, but again, if we want one of these, we're going to learn how to do it and make the calculations in R and StatCrunch. So our decision based on the calculations before would be to reject H sub O, so we have statistical significance. So we are concluding that either this one and or this one and or this one are different for our hospital. Now, if we just examine the sample data, our sample data is 54.3%. That's not a huge difference, but you know, it's about 5.7. 26 point, that's pretty close, and 19.17. So if I were making an estimate right now, I would say that probably it's these two. I would say in this particular hospital that less patients than the national average do not exercise. I would say those reporting sporadic exercise are probably no different. And those that report regular exercise, probably a little higher for this hospital. So more than likely these are, and the way you would follow this up to know for sure is you would run individual one prop z tests that I demonstrate way back in lesson number 1. Seems like many moons ago, right? And I could see if the claim of 60% is true for our sample data, which had 255 out of the 470 report no exercise. All right, super easy to do, and I've already, just to save time, I've already set it up. The observed column, just put in my counts of 255, 125, and 90. The expected is actually the percentages, so this is the theoretical distribution, 60%, 25%, and 15% were no exercise, sporadic exercise, and regular exercise. Here's the command to carry out the chi-square goodness of fit. So we, you know, we do not have statistical significance. I'm sorry, we have statistical significance at the 0.05 level. Now the degrees of freedom are always just our number of groups minus 1. So we have 3 groups that we're evaluating. So 3 minus 1 gives us a degree of freedom 2. And just in case, if you are interested, I'd say you're probably not, but if you are, 7.4 degrees of freedom 2, you can see that we get our p-value there. So we reject the null, and then we'd want to dive in and see where the differences actually do lie. So it appears there's some difference between this hospital and the national report. Now, StatCrunch works a little differently. It works the same with the observed counts, 255, 125, and 90, but we have to put in the expected counts and not the percentages as we do in R. So we have 282, which comes from, let me pop this back to there, that calculation. The 117.5 is the next calculation, and 70.5. The chi-square test of independence, or I'm sorry, the chi-square goodness of fit, as if stats isn't hard enough, me doing crazy stuff. we come down to goodness of fit, chi-square test. So our observed is in observed, and our expected is in expected. And I think we can just look at the expected. Compute this, and we get the same chi-square statistic and the same p-value. All right. All right, gang, that's all I've got. I think, having this in your toolbox is important, but you really don't run into these a lot unless you're doing really a lot of sophisticated things and maybe testing some normality for certain sections of the normal distribution or something like that. But I mean, it does pop up, and I do want you to have it on your radar as a tool that that you can use in research. All right, take care.